All right, we're back live for review, day 3 in preparation of the midterm. I forgot to edit any slides for yesterday. I'll find that and I'll do it. If the normal force and the force due to gravity weight are equal and opposite forces, why are they not? An example of a Newton's third law of force pair is the complete essential question. That's I know out of the view for you right now. We just talked about it a moment ago that a Newton's third law of force pair is going to always act on different objects. And so we'll go over here and we'll state Newton's laws. And after we state Newton's laws of motion, we want to include the language that's going to allow us to sort of remember that little trick there. That even though the normal force and the weight are equal and opposite, because they act on the same object, they are not an example of the Newton's third law of force pair. Rather, the normal force acting up of the table on the block has a force pair F sub n prime of the block on the table. So the force of the table on the block up is equal and opposite to the force of the block on the table down. That prime symbol. The weight acting down has an equal and opposite force, a gravitational force. They must be of the same type, we say. So this is the contact force, these two surfaces in contact with each other. So each of these forces are contact forces. The gravitational force of the Earth pulling down on the object, giving it its weight, is equal and opposite to the force of the block that are pulling back up on the Earth. And so those are both gravitational forces, and they must be of the same type. So the two objects that are interacting for the normal force are the table and the block, and the two objects that are interacting for the weight force are the Earth and the block. And sometimes we forget that the Earth is down, kind of like, well, yeah, of course, the Earth, but we're sort of thinking, sort of just about this. Oh, there's a gravity field, right? Influencing the mass here, right? So weight is the influence of the gravity field on the mass, just how much matter, how much inertia intrinsic to that thing. All right. And that sound means we're moving along. Now let's state Newton's laws of motion to music. Let's write a song. And really, you could do that if you wanted to. All right, state Newton's laws of motion. I think we've kind of gone over these over the last couple of days. Just kind of like that's the way we structured this review. The law of inertia. Inertia is mass. Inertia is mass. Inertia is the tendency to resist change in motion. So those are not stating the law yet, but they're helpful to sort of remind yourself of the academic language there. So we'll say it's called the law of inertia, Newton's first law. And then just a couple of quick sort of notes, sort of about that. Inertia is mass. And we'll say inertia is a tendency to resist change in motion. So it kind of, lends itself to that typical statement of an object that rests will remain at rest, an object in motion will remain in motion, unless acted upon by an outside force. That's why it's kind of the law of inertia, because objects that have mass are made of matter. They tend to resist any change in motion, so if they're moving, they tend to keep on moving. If they're at rest, they tend to remain at rest until those outside forces are upon them. It's not immediately obvious that movement, is just as natural as rest, because there's so many outside forces here on Earth that for a long time, human beings thought that rest was like the natural tendency of things. And objects that were moving were sort of had to be sort of violently disturbed from their natural state, which is rest, and they're trying to get back to that natural state of rest. And that's wrong. That's not the physics. Motion is just as natural as rest. Okay. Objects just move at constant velocity. Some constant velocities are zero. Some objects are at rest, and they'll kind of stay that way. But objects that are moving, they'll keep on moving, right? Until some outside force acts upon them. It's like here on Earth. I switch this eraser, and it quickly comes to rest. It's like for a long time, human beings are like, yeah, rest, that's a natural tendency. You gotta violently disturb something to get it to move, but it's trying to go back to its natural state. And that kind of makes sense to people. The fact that the eraser comes to rest is not due to the absence of my push force, but due to the presence of some other force, right? That brought it to rest, namely friction. I heard everybody say together. Good job. They couldn't hear it on the audio. It doesn't pick up as well in the microphone, but I clearly heard everybody say, "Oh yeah, friction is the force that's bringing that to rest there." And if I want to keep it moving, I've got to equal the friction to push it at constant velocity, which is why we did the friction lab. We had to adopt the procedure of pull it along at constant velocity. You're equaling the friction. If there weren't friction, I should be able to set an object in motion to keep on going forever and ever, right? It's all like, oh, this thing, there's a normal force, and friction slows it down, and gravity, right? Throw something up in the air, gravity brings it down. So let's say, I think we stated this on a chalkboard a couple of days ago. It's objects move at constant velocity, right? So if they're moving, they're keep moving at that constant velocity. If they're at rest, they have the constant velocity to 0. So objects move at constant velocity unless a resultant force acts upon them, objects, them, of subject-verb agreement. An object will move at constant velocity unless a resultant force acts upon it. So that's the first law. The second law, for an object of constant mass, the force acting on it is directly proportional to the acceleration, or the quantities F, force, mass, and acceleration are related by the equation F equals m. And the better way to think about that is force is the rate of change. Remember? Momentum, good. Once again. Oh, I got it. Force is the rate of change of momentum. We'll talk about that. So we kind of revisit these when we study momentum, and we'll review that in its own right on Tuesday. And we'll kind of revisit all these ideas, and so they're all connected, and that's helpful because it's easier to sort of learn it. These ideas don't stand in isolation. So force is the rate of change of momentum is a better way to think about it, and this is a special case of this when mass is constant. So mass doesn't have to be constant, it's just force is the rate of change of momentum. But if, like, it's a block and we're just pushing it with a force, it's not changing its mass. F equals ma, right? The only thing changing is the velocity, acceleration. The mass can change too, and then the rate of change of momentum does that. But a Newton's third law we just spent a lot of time talking about, because the last 2 days we kind of did the first two. And so let's try to get that precise language that we like in physics that allows us to sort of go, okay, forces, what do we say? Of the same type between objects, right? So I don't know if that like of the same type regular. So is there a way to word it like forces between objects exist in pairs equal in magnitude, opposite in direction, and they must be of the same type. We can put that at the end. I kind of like that a little bit better, but as long as you include that information, it's like what makes sort of better sense to you. I'm gonna word it like this. Forces between objects, and like underline that X, you have to, or make an explicit note. Forces always exist between two objects. It's always true. When you walk, you're pushing on the earth is pushing back on you. All right, so forces between objects exist in pairs. The forces occur simultaneously. So the language doesn't do the physics justice when we say, for every action, there's an equal opposite reaction. But that's typically the way we learn Newton's third law. And that's fine if it helps you sort of get to the idea of our language isn't good enough to say, like, forces occur simultaneously and they exist in pairs. It's like, oh, there's an action and then a reaction. They occur simultaneously. The forces between, and that's really important to paper 2 questions we've been answering about. The time that they're in contact is the same, right? It's not like, oh, one acts on it and this one has to react. time later, the time of collision is the same, right? And so if the force is the same because of this law and the time of collision is the same, then the change in momentum is going to be the same. So like all these sort of laws built on. Every time you say, like, why is the momentum of this object, the change in momentum of this object equal to the change in momentum of the other one? Because the force between, those are the two objects interacting. So the force is the same, the contract the same amount of time, the change in momentum is definitely the same. Forces between objects exist in pairs equal in magnitude. So force is a vector, the magnitude is how much, it's 10 newtons, 20 newtons, 30 newtons, right? So equal in magnitude. Opposite in direction, so vectors have direction. Gravity always acts down. Also, furthermore, they must be of the same type. And you could say like forces of the same type, but then it's kind of like, you have all those qualifiers. Like you get to the heart of the law. The forces exist in pairs, but they are between objects. Okay, and, these forces are of the same type. Okay, so gravity forces is another gravity force. A contact force is another contact force in another object. A nuclear force is another nuclear force. Okay, of the same type. Identify the forces acting on a body in different situations. So you can kind of think about what are all of the different forces that we've sort of been able to identify throughout the year. And some of them we've talked a lot about because they're very common, like weight. Things have mass, they have weight. And other ones are maybe not as familiar to us because we just haven't, seen a lot of sample problems with them. But we want to be sure to cover as many of them as possible. So let's go through our notes. Let's brainstorm together. Let's sign on the door. Danger, brainstorm in progress. Do not enter. Oh, I got stuff on my testing. Do not disturb. Testing up for one more time. So let's say force due to gravity, weight. All right, so weight equals mg. We have an equation for that one. Any other forces we can think of? Let's get the ones that we've already kind of listed here. So the normal force, okay, contact force. How about friction? The force of friction, and we'll find an equation for that one too. Remember, it's equal to the coefficient of friction times the normal force. Tension, it's like the force in a string. Okay, we usually use capital T for that. So got tension forces, friction, weight, normal. Well, we talked about the drag force, right? So like friction with air, drag. Okay. But it is just a resistive force. Sometimes they'll sort of combine these together and they'll say, like we saw with the example problem with the car going along, and the resistive forces acting against it. Well, like friction, those are all resisting the motion. How about this one? We haven't spent a lot of time talking about this one. Up thrust. Up thrust. The buoyant force. Up thrust. Okay. Buoyant is part of the stuff. That's right. Buoyant. Buoyancy. So up thrust is really like what makes a hot air balloon float, or what makes a ship, float in water. There are collisions with particles with an object, say that's like floating in the sea. The deeper down you go, the more density there is. The water is more dense. There's more mass per unit volume. And so mass is the amount of matter, and kinetic molecular theory suggests that matter is all moving around. And so there's more collisions on sort of the underneath side of something than there is sort of at the top of it, and that creates a net force up. And so it really is what sort of leads to buoyancy. You say, well, how could a ship float if it's got weight? Why doesn't it sink? What's the force that's going up there, right? Like the up's got to equal the down. If a boat is floating, it's not accelerating down like the wave wants it to do. It's not like there's something magical about the water. It's like there's no gravity if you're over water. It's like it's still on Earth, there's still gravity, right? See, this is much gravity there, good. Okay. Oh, then you can't see. Just as much gravity there in the water as there is over here. See those vectors very clearly drawn, very strong. Right, force out the line. So up thrust. Okay. If you had an object with weight, and it's sinking through a fluid, okay, like you drop a marble in oil, right? And the oil is going to exert a viscous force, okay, viscosity, fluid friction, the drag force, viscosity, another force, of fluid friction, and drag. There's a resistive force opposing its motion. There's also going to be an upthrust force, okay, because that liquid, okay, has more, again, greater density, the further down you go, more particles, and so there's this upthrust force. And so a typical question is like, well, the resistive force and the upthrust, they must equal the weight if this thing is just sinking down at constant velocity, okay, or an object, falls through the air. Sometimes you only consider the weight of the drag force, but there's also an upthrust force you're acting on. So keep that close. And we'll see questions about it. The reason why I'm kind of focusing on that is we kind of have been focusing more on the other ones, but there's a number of sample questions where it's important to be able to explain this. State the origin of upthrust. You have to be able to account for it with the compass. And again, when we study momentum, we talk about this, idea of a particle colliding with a wall and changing its direction. The wall exerts a force. And so it's like the collective impact of all these particles down here, and there's more of them crashing on the underside up here, the deeper down you go in the fluid. Okay. There are applied forces, right, a push or a pull. And we'll probably think about it. Okay. So just being able to sort of look at an object and say, okay, these are the forces acting on it. Let's add them up, right? We want to be able to sum the forces, because how do we describe how the motion of a body is affected by the forces acting on it? This is really sort of the power of physics. This is when we get to, okay, it's somewhat powerful to be able to predict changes in motion kinematically, like things are moving and I can predict where it's going to be, how long it's going to take to get there, all sorts of things that, the sort of the power of science, the ability to predict. But dynamics is even sort of greater power. Because now we're sort of able to predict how an object is going to move, like before it moves. Like if all these forces are acting on it, then we can anticipate for the direction it's going to accelerate, how much the acceleration is going to be. We know what kind of forces we're going to need to achieve, certain movement. And so we can kind of, if you look at the slides, that belong with this one, I really kind of like to think about it in terms of Newton's second law here, how the motion of a body is affected by the forces. It's the sum of the forces, or the net force, or the resultant force, right? So the left side of the equation, that equals the mass times the acceleration. If you add up all the forces acting on it in like one direction, you can anticipate how it's going to accelerate in that direction. And if you do the same thing in other directions, right? Add up all the forces in the x-axis and the y-axis and the z-axis, which we don't usually do in this class, because two-dimensional physics is tough enough in 1, 2, 3, or 4, but we can add as many dimensions as we need to. Even, hypothetical 5th and 6th dimensions, if there are forces acting, whatever that might be, kind of hurts my mind to think about it. But 3 dimensions, that's not too bad. We can kind of look in the corner of a room and go, okay, length, width, height, 3 spatial dimensions. There might be forces acting in all of them. And I can treat each dimension independently, kind of see what's going on. Add up all the forces. If I know the mass of the object, it's a constant mass. I can calculate its acceleration. What is acceleration? It's the rate of change of velocity, so I can anticipate how the object is going to either change its direction, right? Its velocity is a vector, or how it's going to, speed up or slow down. And that really is describing its motion, okay? Like which direction it's going to be going in and how fast. Then we kind of know, where it's going, how fast it's going to get there. So this is sort of like the general foundation of, how we would describe the motion of an object is sort of very mathematically. And then working with sample problems, it makes it a little bit more real. We're saying like, okay, well now let's start doing this. Let's add up some forces, acting on an object with calculated acceleration. But just kind of know that we can really boil this down to sort of basic ideas that we've already defined. It's like, oh, motion could be described all sorts of ways, poetically in an English class, and you could talk about, ballerinas, but it's like in physics, all we're saying is that bound is accelerating. Okay, changing direction and speed. It's like just the most boringest technical writing, it's like when we write a lab report, we're not trying to be creative. It's like, here's what I was testing, here's what I got, the end. And it's safe and creative writing for English class. So it's like, we don't care about all the, I'm not trying to like take away from like the beauty of nature. It's like Feynman, my favorite physicist of all time. He was once said like, oh, you scientists, you break something down and you take the beauty out of it, An artist looks at a flower and they see the beauty of nature. You scientists, you look at it and you see the cells and and you take away, and Feynman was really critical of them. He said, oh, I don't lose any of the beauty in a flower. In fact, I appreciate it more because I kind of know how interesting it is, what's going on there. So I'm not trying to say like, you can't sort of appreciate, sort of the beauty in nature through the lens of physics, or to subtract from it or like take away anything. But what I'm saying is what we're trying to do with this stuff is just sort of the very basics of it. Like we don't, at first, we don't really even care about the shape of an object. If I throw 2 things across the laboratory, it's always my favorite to throw a ruler, the shape of these objects affects their motion, like a ball, a dart, I can't even see that, a marker, a ruler. They all kind of move differently, through the lab. But at first, we don't really care about that. We're just like, it's a point-like object moving through one-dimensional space. So then we say, what about 2 dimensions? It could accelerate in this dimension and just stay constant over here. But still, we don't really care about the shape of it. Until we get to a little bit more sort of, complex. And I say, oh, well, now the cross-sectional area affects the drag force, right? Like the more surface area it has, it can catch more air. That's how a parachutist can parachute again. Because the drag force is so pronounced that it can sort of overwhelm the weight that brings the skydiver down, and they can, drop down to a safe enough landing speed. So like we can invent technology based on our understanding of this and go, hey, we can skydive and do it again. Okay. So it is a powerful way to sort of think. And again, this is just sort of being able to explain like, okay, this object moves this way. That little bit of discussion made me think of a great read here. And Dr. Wilczek is not paying me to promote this book. A beautiful question. Finding Nature's Deep Design. So Frank Wilczek, he won a Nobel Prize in Physics a couple of years ago for his work in quantum chromodynamics, which really is a discussion or is some discoveries made with nuclear forces. Let's not forget about those. Nuclear forces, electrical forces. All right, so the strong nuclear force is governed by, field called quantum chromodynamics. And Dr. Wilczek, did some important work with that and published this book there and just kind of show you. Kind of this guy here. Okay. It's like three gluons or three quarks sort of bound together in the nucleus that sort of make protons. And why is the sort of the strong nuclear force so strong? All right. Connected, right? Nuclear forces, those are forces, and so they sort of keep the protons together inside of the atom. We trust the physics so much that it's like once we observe something happening, then we say, oh, there must be this other type of force. Because if we knew that there's electrical forces, and we say, okay, well, the first sensible model of the atom was to, once we discovered electrons, J.J. Thomson discovers electrons in 1890, they say, well, there's got to be positive charge in there, because atoms are neutral, so if there's negatively charged things in everything, electrons and all sort of matter, got to be positive charges in there. It's like a plum pudding model, right? Like a big massive positive charge or negative sort of plums put in the pudding. But then some more careful experiments were conducted. It's like, no. All the positive charge is like really, really tiny in the center of this atom. Like all the positive charge is stuck together in the middle, and most of the atom is just emptiness. This is the alpha scattering experiment or the gold foil experiment, Rutherford's famous experiment. And so the fact that all of the positive charges are together in the nucleus is like, that violates what we know about electrical forces. Like charges repel. Why does the nucleus just explode? Why don't all the protons repel each other and everything just, like clearly matter exists, we're not all exploding. So, I don't know, a nuclear force is stronger than, we'll just invent the force. The nuclear force, it must be stronger than the electrical force. It is the force that keeps the nucleus together. There you go. And that's kind of the way that, scientists go about their work. They say, there must be a force stronger than the electrical force. Otherwise, we wouldn't be here. If you consider this question, right? Like no matter would exist. And so there's got to be nuclear force. And then Dr. Wilczek does some work and says, yeah, here's how it works. Quantum thermodynamics. And it's really fascinating, if you ever want to sink your teeth into that. And of course, it's not, it's a physics book for sure, but again, think about the title of it, a beautiful question, finding nature's deep design. So he sort of talks about, can scientists sort of get to this idea of beauty in nature, and it's really fascinating. All right, so we're kind of getting over here, like we're using Newton's second law as a way to sort of make sense of this learning objective. This is solve problems using F equals MA. Let me show you my favorite solve problems using F equals MA calculation of all time. I don't know if you all are ready for this. Ian, are you ready? Okay. Oh, they must be communicating in the chat. Yeah, what's going on? Everyone's participating. Solve problems using F equals MA. Here's my favorite calculation of F equals MA of all time. And it's a segue over here to this chalkboard. Okay. How much force is required to accelerate a 1 kilogram mass 1 meter per second squared? So I have a 1 kilogram mass. Do I? Where's my kilo? I do have a 1 kilogram mass. Okay. And what is the force required to accelerate it so that it picks up 1 meter per second of speed every second? How much force is required? 1 Newton. 1 Newton of force is required to accelerate a 1 kilogram mass 1 meter per second squared. Unfortunately, they only get harder from here. Like my favorite is the easiest one. Why do I like that one? Because I like calculating with one. I like calculating with zeros too, except for dividing by zero. I don't like that. But, you know, timing by zero, or zero in the numerator is okay. Dividing with zero. So why did I say that this is a good segue to the end of the base units? Because it really does define what a Newton is, right? So a Newton of force is a kilogram of mass times a meter per second squared. And we derived this unit from base units, right? So scientists say, let's just define as few things as possible. Scientists are looking to simplify and unify. And there's a rich history of that in physics. One of my favorite, sort of stories in science is James Clerk Maxwell reasoning his way through electromagnetism and saying, well, an oscillating electric field creates a magnetic field at a right angle, but then that magnetic field in turn creates an electric field at right angles to it. Well, you could have electromagnetic waves traveling through space. And how fast would they travel? And he calculates in his laboratory the permittivity of free space, the permeability of free space, things he could measure in his lab to calculate the speed of these electromagnetic waves. And he gets an answer that is like the known speed of light. So scientists have already determined the speed of light before James Clerk Maxwell sat down and did his calculation. And no one knew that light was electromagnetic. No one had any idea that light was an electromagnetic phenomenon. Maybe they did. But James Clerk Maxwell kind of proved it right then and there. He said, hey, these electromagnetic waves travel at the speed of light. They are light. Light is an electromagnetic phenomenon. And there's this great simplification that we got. Even understanding that electricity and magnetism are two sides of the same thing. Like there's electrical forces, there's magnetic forces, and they're really kind of the same. Okay. So, a simplification of electricity and magnetism. There are fundamental forces. That's another thing that we sort of haven't talked about, but we did, sort of when we covered this earlier. There's only 4 fundamental forces actually listed. There are 2 of them are nuclear: the strong nuclear and the weak nuclear. Gravity, force due to gravity. Wait, so we do have, them there, and then electromagnetism is the force. So I guess we do have fundamental forces are accounted for on that list over there. So we only want to define as few things as possible. So scientists say, well, 7 base units. Okay, we'll solve more problems with F equals MA for sure. Like I said, we'll start with the simplest one and then add some difficulty to that. And we'll try to do some sample problems before the end of the class here. This is about 10 of 7 in this class. It's about 20, 30 minutes done. I'm not gonna. You all can check, my YouTube channel at the end of the day or between now and the midterm. Go over different sample questions in different classes, and so some of the sample questions we might go over are different than theirs, but I record them and upload them so that way we can cover more practice questions, and it's kind of up to you to avail yourself of that and help if you need, extra sort of practice. All right, so. Get the whole board. Yeah. Come on, Candela. There's probably Candela. Never even use it. All right, so we redefined the kilogram a few years ago. I think amp is next. Okay, I think amp needs to be redefined because it's like impossible. If you have 2 wires of infinite length, it's like, okay, let me go. There's some infinitely long wires and stuff out in my laboratory. So that's the kind of way we have to define Okay, so we have the base units, a complete list of all 7 of them. Meters, kilograms, seconds, amps, Kelvin, volt, candela. Mister, kilogram, saw, kangaroo, man, factor. You can use that mnemonic device if it's helpful. You need to know what the 7 base units are, because you have questions that'll say, the meter and the kilogram are 2 base units. State 3 others. And say, oh, they already took the 2 easy ones. You gotta, you have a way to sort of know what are some other ones there. And so this is the quantities that they measure, right? Meters measure distance or displacement or length, right? So linear dimension. Kilograms measure mass. Seconds measure time. Amps measure electrical current. Kelvin measures temperature. Moles measures amount of substance. And candelas measure luminous intensity or brightness. Okay, brightness. It is more typical to have the derived unit watt. Explain luminous intensity, like 100-watt light bulb, how bright it is. Okay. Well, I should be more careful. Watts are the power. Okay, the rate at which energy is converted from one form to another. You can have a really bright 15-watt light bulb. Okay, because it's like an LED. All right. So in other words, a 100-watt light bulb is bright. It consumes a lot of power, 100 joules per second. A 15-watt light bulb could be just as bright. It's just consuming less energy because it's more efficient. And on Monday we'll talk about work, energy, power, and remind ourselves of efficiency. So I should be very careful. But we do tend to measure like the brightness of the sun in watts. Okay, it's luminous intensity in watts because it's a power, right? That the sun is converting nuclear energy into light energy, heat energy. All right, as I mentioned, we have to kind of know these orders of 10, and there are more metric prefixes than just these. Peta, exa, yada, zeta. There's really tiny ones, octo, femto, atto. Okay, like 10 to the negative 24, so they get a lot lower. Okay, but you need to know these for this course. These are the only ones that they'll really you'll see on like a paper 1 or paper 2. And if you had anything, sort of bigger or smaller than that, they would give it to you. A femto is 10 to the negative 15. Like the next one down is a femtosecond, an attosecond, 10 to the negative 18. Zecto, yocto is the smallest. Yocto is 10 to the negative 24. So again, a yoctometer would be if I divided this meter into yoctometer would be 10 to the negative 24 meters. So 0. That many meters is a yoctometer. You have to divide the ruler into what? Million, billion, trillion, quadrillion, heptillion, hexillion, septillion, heptillion, 1 heptillion sections. Just divide this here ruler into 1 heptillion sections, if that's a number, septillion. And each one of them is a yoctometer. Okay, so just divide this into a septillion equal sections. Each one would be a yoctometer. So you get the idea. You get really, really small, okay, because some things are really, really tiny, quantum mechanics, okay. And then we study like the universe as a whole, cosmology, that's a field of physics. So we need really big numbers, like space, the number of atoms, and we kind of use moles for that. A mole is a lot of things, right? 10 to the 23. In fact, the midterm is on mole day, 10 to 23. I don't know about for you guys. Do you think your midterm on Friday or Thursday? I can't remember. Good luck. You guys are right. The mole day. We got a mole day exam in here. All right. And remember, I have to remember, you get 40 questions, but I'm only grading it out of 20. So it's possible you could get 40 questions out of, no, I'm grading out of 22. There's 22 questions, I think, that I've already kind of prepared. So maybe I'll give you another 22. Maybe like out of 44. We gotta do it. One out of 23 for Molden, because the midterm's on the 22nd and 23rd. This will be good. Because I don't believe in any kind of superstitions, numerology, but just because I don't believe in it, it doesn't mean it might not be true. Like, it might be true. And so I like, even though I don't believe in it, I still kind of want to, practice it, if that makes sense. Because just in case I'm wrong. Like, it could be that, like there's some like, my lucky stock, I always win, when I'm wearing it. It's like, I don't believe in any of that stuff, but what if I'm wrong? I want to make sure if they are lucky, I'm wearing it, like, even though I don't believe that they're lucky, I'm still going to give myself the opportunity to avail myself of that good luck, if that makes sense. So I think it's good luck here if we have a midterm of 22 and 23 questions because we're taking the midterms on the 22nd and 23rd. Okay, that's just my way of thinking. Kind of crazy way of thinking, and that's true. I think go another part. I think a little bit different. Let me further elaborate on what I do. What's your golden birthday? The golden birthday is when you turn the age of the day you were born. So some of you may have already passed, you didn't even know. I was born on the 3rd, I was 3, I didn't even know. My golden birthday. Does anybody have a golden birthday not yet come? Or they already have theirs? What will be your golden birthday year? What day of the month were you born? The 20th, so you're 28. I'm looking forward to it. Okay, golden birthday year, 28. Anybody else want to share? The 4th, you're like, okay, when I was 4, came and went, didn't know. And, it's like, no, stuff. But it's like, I'm gonna make up for that. I'm gonna do something on my 24th. Anybody else that want to share my golden birthday? I was born on the 23rd. I think we all remember, like, multiply meters per second by my birthday, February 23rd, you turn in miles per hour. It's really unfamiliar. You're like 45 meters per second. We just calculated the velocity. It's just like, is that fast? I don't know, 45 meters per second. I don't know. Multiply it by my birthday, 2.23, February 23rd, and you'll realize that that's kind of fast, 100 miles per hour. So that's the conversion that converts meters per second to miles per hour. All right, you two gather around and I'll tell you the story of my golden birthday. Unless there are any other stories of anybody's birthday before I begin mine. On my 22nd birthday, the movie starring Jim Carrey came out called The Number 23. There's a movie called The Number 23, and it came out on February 23rd when I turned 22. So on my 22nd birthday, I told my wife, on my birthday 1 year from now, when I turn 23, I want to watch the movie, The Number 23, starring Jim Carrey, which is sure to be out on DVD by that time. Because again, it was released on my 22nd birthday. So a year later, it's going to be on DVD. I already got plans for my 23rd birthday. And my wife said, you're not going to remember that. I said, how could I forget? It's my birthday. It's the number 23. It's my birthday. There's no way I'll forget. And sure enough, 1 year later, that's what we did. I guess it's really not the story. I remember what I did on my 23rd birthday because it was the number 23. And that movie is all about numerology, how the number 23 shows up everywhere, and it, governs our whole life. So check it out. And then at the end of the movie, they do go through like a little mini documentary of numerology, and some people really think today's date, 10:15. Well, that's 1 plus 0 plus 1 plus 5. That's 2 plus 5 is 7, and 7 means something is going to happen. I don't know. And so, like when we teach astronomy, the very first lesson is this is not astrology. Like, are you in the right class? This is not a pseudoscience. This is the science of astronomy. And the history of like astrology and astronomy is fascinating to sort of examine. Kepler, great scientist, he was an astrologer. He read people's horoscopes. People believe like the motions of the planets are lives or something like that. I don't believe in that, but just because because I don't believe in it doesn't mean it might not be true. I'm just very scientific in the way that I think, and so I want things that are testable. And I just accept the fact that certain questions, which are fun to think about, they're entertaining to they're important questions, are beyond the scope of science. The science will never be able to get to them because there's no experiment will ever be able to design to put some of those ideas to the test. So do not limit your horizons by only thinking about things scientifically. There are other ways to know and understand the universe, but we have to be very restricted in sort of what we consider scientifically because it has to be testable. And as soon as we get sort of a hypothesis that is untestable, don't be so quick to give up on it, but just sort of recognize that, oh, this might be beyond the scope of where science is at right. When Galileo's student, Galileo said, it doesn't matter how massive things are, I drop them, they fall to Earth at the same rate. One of Galileo's students said, well, what about a feather and a hammer? Drop a feather and a hammer, one will certainly fall to Earth at a slower rate. And Galileo said, that's true, but only because of air. On Earth, there's air, and the air sort of creates that drag force, right? It's kind of, the same idea we're talking about. We can describe the motion of a feather because there's other forces besides just its weight, right? There's a pronounced drag force. Or a hammer wouldn't have that much of a drag force. Still a drag force, but not too much, right? And so Galileo hypothesized, if you were to go to the moon where there is no air to drop a feather and a hammer, it would indeed fall at the same rate. And that's an experiment that was conducted by Apollo astronauts hundreds of years later. So it took a few hundred years. It would say, that's not scientific, Galileo. That's not testable. We can't go to the moon and test your idea. Well, not yet. Okay, have a growth mindset. Okay, one day we'll get there and we can test it. So that's why I say, like string theory. String theory is famously difficult to test, but it may be like the grand unified theory. It may be the theory that combines all those fundamental forces that I mentioned. Strong nuclear, weak nuclear, the electromagnetic, and the gravitational force. Gravity is super tough to unify because it's so weak. It always attracts, like the other forces have like a repulsion, like electromagnetism. It attracts and repel. Gravity is always attracting. A few years ago, there was a researcher named, always out of Oxford. My apologies. His name was, I can't recall, but it's a really fascinating paper that he wrote about negative mass. Hey, if you have negative mass, that might explain dark matter and dark energy. And he wrote a whole paper on it, and it's like, yeah, this paper is just kind of like a work in progress at this point. Now I kind of did some calculations. It is true, it'd be kind of cool because I've just figured out what dark matter and dark energy is. He kind of posited negative mass in the universe. So I mean, kind of well beyond the scope of this physics course, but something to look forward to. Pretty fascinating stuff. Jamie was his first name. Remember that. Jamie something from Oxford. Okay. So that kind of gets us to the end of this chalkboard over here. I've got 4 derived units, and these are the ones that I can kind of think about, like, okay, we talked about force, energy, power, pressure. We got to have equations to get them down to the base units, and then we can kind of look at some sample problems, both with solving F equals ma, looking at homogeneity of equations. Oftentimes with this, we're sort of checking to see if the units are the same on both sides of the equation. And so these are the types of learning objectives that sort of lend themselves to, let's do some practice problems, let's see how well we sort of master this. For the next part of class here, let's take a look at that. We've still got a couple of minutes left. Or, let's just do one more, because we did one at the beginning of class. Let's look at one more here. Okay. Projectiles. I'm sorry, I just now saw the chat. Was there a certain part of the board that you needed to see? Or was that just like a comment from a while back that I just missed? One practice problem. We're in the class one more anyway. All right. It says a driver stops his car in time t by gradually increasing the total braking force on the car. The graph shows the resultant force on the car. So it's like he pushes down harder and harder on the brake pedal, right? So it's like he's increasing the force of the brakes, okay, as a function of time. Let's just kind of think about what is force? The rate of change of momentum, okay? And we know that force equals mass times acceleration. So the force is proportional to the acceleration. The more force, the more acceleration. Or in this case, the more deceleration. So we're trying to now match this force against time plot. And the area underneath it would give what? Force times time. Impulse, remember that? Impulse is the product of force and time. So like, remember the area problem, okay? So we're looking at a speed versus time plot, kind of like a velocity time graph, but they're saying like, we don't really care about the direction, it's just the magnitude of the velocity, the speed. So which one of these graphs of speed against time correspond with somebody pushing the brakes harder and harder and harder on their brake pedal, right, as a function of time. So it's like, when you first push the brake pedal, you haven't exerted as much force as a moment later when you slam down on it harder. So that's just kind of like pushing the brake pedal. What happens to the speed of your car? Does it decrease like this until you're at a speed of 0? Does your speed decrease like this, just uniformly? Does your speed do something kind of crazy like this? Okay, this curve here in C, which kind of like goes, and then this one that's like that. So any hypotheses, any thoughts on this? Well, there's 3 minutes left in class. Let's finish strong here. Somebody offer an answer. Say it again. D is correct. D is correct. Well done. What was your thought going into that?
It sounds like if they're pushing the brake harder, then they're going to start accelerating faster, and it's going to accelerating faster.
Yeah, remember we talked about interpreting a displacement time graph. We said it's going to be like a curved line, okay? If the force were constant, then it would just be like a straight line like this, like one value of force. And then we get this constant slope, right? When force is constant, we get a straight line, right? And the slope of that gives the acceleration. Here we have a variable force. The force is changing. And so we would expect a curved line on a speed time graph or a velocity time graph, or indeed the way that Brad explained it is correct. It's losing most of its speed, right, when the greater force is applied, right? Because the acceleration is proportional to force. So it's decelerating more here. And so you see how it trails off quicker, right? It's not just a constant thing. This would be if it were a constant force. I don't really know what kind of universe this is, okay? But this is correct for the physics that we. This would be like, it starts to slow down, but then the rate at which this is like the way I think that you want to brake. This is the way you should drive, gradually coming to rest, okay? Not jamming on your brakes, and then it costs you, more fuel to get the car moving again. Like come to a coast, so you want to gradually kind of reduce the speed. You can just let off the brakes and the resistive forces and make it come. So remember, I'm out there sharing the road with you. We'll call it a day there.